Hello everyone, welcome back to another episode of Marin Maths. And on this video, well, first of all, I have to say I'm very thankful, okay, happy Thanksgiving Day. I'm very thankful for you guys to be here, okay, watching these videos that hopefully you might find interesting or useful for whatever subject you're doing. If you're taking a math class like Math 112 or 111 or Physics 111 and 121, and you have watched my videos and maybe you found it interesting or useful, right? If it helped you, boost your grade, well, I'm very thankful for that. I'm happy that I'm able to help you out. That's what I'm here for. And well, I'm also thankful for, being able to do these videos, because really, this is what I love to do. I love to do math and physics and wonder about things, That's what we're here for. So thank you all, and keep watching, okay? Subscribe if you haven't. And also thank you, Nick Dubicki, since you just became my first patron on patreon.com. So that's a big plus for me, and for you all as well. Thank you. Anyways, let's get started with this over here. So in Calc 2, okay, Calc 112, we learned, a bunch of things that are very math heavy, right? Like methods of integration, stuff like that. But I think, okay, the most important of all topics that we learn in Calc 2 is, well, Maclaurin and Taylor series, because these are probably the most practical tools that one can use in any technical career that has to do with science, okay, or math, right, engineering, all these things. Because, well, Maclaurin and Taylor series can help people, okay, approximate values for functions, okay, that are, defined in some interval, right, but are kind of hard to, okay, write out by hand. So usually polynomials are much better to work with. So that's why Maclaurin and Taylor series are useful at all, right? But now, it is known that Maclaurin and Taylor series can approximate, okay, any function using a series expansion, right? Almost any function, but not all functions, because what's the catch? Well, in the Taylor, okay, series theorem, there is a very specific restriction that doesn't allow us to actually approximate the values for any function, okay, like this function over here. F of x equals cosecant of x. And well, the thing is, for a Taylor series to be, okay, found, for the expansion series of a function to be found, you need to have a function that is differentiable, okay, and it has to have derivatives of all orders, and it has to be differentiable on the interval that you're trying to approximate, okay. For instance, if I try to find the Maclaurin series of cosecant of x, say when x equals 0, right, which is just going to be the Maclaurin series, right, then we will have to, okay, account for the differentiable, the differentiability of the function at this value, right, at x equals 0, or around x equals 0, because that's what we're trying to look for, right? We're trying to look for a local approximation around x equals 0. So it does not really work for cosecant of x, does it? Right? Because if you think about it, if we try to graph cosecant of x, right? If we try to graph cosecant of x, okay, we're going to have something like this. This is bad x-axis. We're going to have, okay, something like this. So we're going to go from infinity, okay, down over here like that, and then up. Right, and then the same goes over here, something like that, and then it just keeps on going. So you keep having asymptotes. So there is asymptotes over here, right, where the function is not defined. So this is okay, a sketch of cosecant of x. And what happens is, if we try to approximate, okay, the value for cosecant around 0, okay, we're just going to get a really large or a really, okay, small number, right? And so we cannot really use Taylor series approximations for this, because we don't have derivatives at this point, right? And that is because, well, the value of the function at 0, right, f of 0, is not equal to the limit, okay, of the function at this point. okay, of f of x as x approaches 0 from either right or left, because this limit, okay, does not exist. So if the limit of the function is not equal to the value of the function, because the value of the function, well, is undefined, then it's not continuous, it's not differentiable, okay? So what can we do? What can we possibly do if we can really approximate it? I mean, we could probably use a Taylor series expansion for, say, if you want to approximate it about pi over 2, right? X equals pi over 2. You could do that to some extent, right? There will be a point where you can no longer take derivatives, or the values of the function will not be defined, right? So let's see what we could do here. So one thing I was trying to do was, well, let's see if maybe we could use a very well-known series, right? So what if we rewrite this, okay, over here? So we rewrite f of x, okay, which is cosecant of x. We can rewrite it as, okay, 1, right, divided by sine of x. And here is the issue, right? When sine of x evaluated as 0 is 0, then we have 1 over 0, okay, which is undefined or just infinity, right? It will just approach infinity, right, as this goes to 0, as x goes to 0. So I was trying to, okay, think about a very well-known series derived from the Taylor series, right? Because we know the Taylor series, right? The Taylor series is just, okay, the sum, okay, from k is equal to 0 to infinity of the kth derivative at around some value a, right, times x minus a to the kth divided by k factorial. And so we cannot take derivatives, right, for this at when a is equal to 0, right? We cannot take derivatives. So what we're going to do is we're going to use a very well-known series. So this looks like, okay, this looks like something we could compare it to, like 1 over x, right? Why not? This is pretty similar to this, right? It's 1 over something, 1 over x, right? We've compared it to 1 over x, okay? This is very similar, okay, to say 1 over 1 minus x, which is just a power series, right? A convergent power series. So this is going to be the sum from k is equal to 0 to infinity of x to the power of k, right? And then we're going to have a convergence of the absolute value of x, which is less than 1. All right, so we use this very well-known series, the power series. Black pen, red pen actually calls it the best friend because it's so useful. Then we can manipulate this expression so that we get something like this, right? So we get something like 1 over sine x. So let's see what we could do. We could do, okay, 1, okay, if we just do direct substitution, right? If we just do a direct substitution, we can do 1 over, okay, 1 over x, or 1 over x is just going to be 1 over 1 minus, and then over here we have to input something so that it looks like 1 over 1 minus x, but then when we simplify we can just get 1 over x, right? So how do we get rid of the 1 over here? Well, we just subtract 1, so we put 1 in here, right? And then to make x positive, since we already have a negative, we just subtract an x inside, okay? So this means that it will be the series, right? It will be the series, the sum from k is equal to 0 to infinity of 1 minus x to the kth, okay? Which converges for the absolute value of 1 minus x, which is less than 1. All right. Now, this over here is just going to be a power series, and we can use this, okay? We can use this for sine of x, right? So we can do the following, right? We can actually just substitute this x, right, for sine x. So if we substitute this x for sine x, all we're going to have, we directly substitute it in there, and we have the sum from k equals 0 to infinity of 1 minus, and then we do our direct substitution in there, so we get 1 minus sine x, so the power of k, okay? And it's convergent for 1 minus sine x is less than 1 in absolute value. Now, this over here is actually, you know, the series expansion for cosecant of x. But the problem is, you know, the whole point about expansions, series expansions, is so that you get something that is easy to manage, right? Something that's easy to calculate. Polynomials usually are the choice. So we could kind of reduce this over here. We could kind of reduce this, right? We could expand it. Actually, we could expand it because we know that the series expansion for sine of x, right, is just going to be x, right? Sine x equals x minus, right? Don't forget the minus x to the power of 3 divided by 3 factorial plus x to the power of 5 over 5 factorial minus dot dot dot. Okay? So this is the series expansion for sine x, which is just the sum from, okay, n equals 0 to infinity of x to the power of 2n plus 1 divided by 2n plus 1 factorial. And then don't forget that you have an alternation of signs. So first you have a positive sign, then a negative sign, positive sign, negative sign, and so on. So you can express this as negative 1 to the power of n. Okay, so that's the series expansion for sine x. So finally, we can say that, okay, the series expansion for cosecant of x can also be, okay, the sum, right? The sum from k equals 0 to infinity of 1 minus the sum from n equals 0 to infinity of x to the power of 2n plus 1 divided by 2n plus 1 factorial. Okay, and then all of that times negative 1 to the n, which is just the alternator, and all of this is raised to the power of k. And this is a pretty hairy expression, you know. Look at this. Like, okay, don't even try calculating the first terms for this. It's just too much. Okay, so you know, I came to the conclusion that, well, I mean, this is at least a good attempt, right, in trying to find a series for this. But here is the issue. Okay, the issue with this is that this only accounts for all positive values of cosecant. So that's an issue. And you know, when we're missing half of the answer, then I mean, you could kind of just say, okay, well, you could manipulate this to get the other half of the answer, but that doesn't mean you derived it mathematically, right? So it's not really correct to do that. It's not mathematically proper to just, you know, change the answer at your convenience, all right? But if we were to do that, right, this only accounts for the positive values of cosecant of x. So this is just going to be, this is going to look like this, okay? This is going to be something like that, and then like that, and it's going to skip the values that go over here, okay? So these values on the bottom, okay, on the negative side of the y-axis don't exist in this series. And I'll show you in the graph that I'm gonna show you on Desmos in a second, right? But now let's consider this, and now let's consider, okay, what could possibly be, okay, the other series, okay, a series that represents the other half of the answer over here, right? So here, you know, that's the issue, and well, I was going to touch on complex numbers, right? But let's not do that yet. If we want to find, okay, a series representation for the bottom part, well, all we have to do, okay, this over here is pi over 2, right? And this over here, okay, is negative pi over 2. So what is the distance, okay, the x distance from here to here? Where we'll do d is equal to pi over 2 minus pi over 2, which is pi. So, and also, what happens when we want to bring this down? We want to reflect this graph, okay, across the x-axis. Well, that's just basically a multiplication by negative 1, right? So what we could do is, we can take this series, we could multiply it by negative 1, so we have the negative series from k equals 0 to infinity, right, of 1 minus the series from n equals 0 to infinity of, okay, and now over here we're going to shift the graph pi units to the right. So we're going to have to make a transformation in the x, so it's x minus pi to the power of 2n plus 1 times negative 1 to the n, okay? And then all of that divided by 2n plus 1 factorial, okay? And all of this is raised to the power of k. So this accounts for the lower portion of the function, cosecant of x. And it's pretty okay, curious to see that it actually works. So I'm going to show you on the graph in a second. But you know, the actual answer to this problem, if you derive it with really you know, high mathematics, it's going to be something in terms of a complex number I, right? And so that just touches onto a whole different area of mathematics, to which I'm not very familiar with, right? I don't have the tools, the mathematical tools to okay, talk about, you know, the complex analysis world, the complex analysis realm. But I'm going to show you what it is. So it's basically, they use something called a Laurent series or a Q series, right? So the answer to that will be something like this. It will be cosecant of x, right? Cosecant of x is just the series, okay, negative 2 times the complex number I times the sum from k equals 1 to infinity, okay? And then we're going to have q to the power of 2k minus 1, all right? And then the case is that k, I'm sorry, this is q, right? Q is equal to e to the I theta, or ix, okay? And so, you know, ix is just going to be Euler's identity, right? So ix is just Euler's identity. So you could just rewrite this as negative 2I times the sum from k equals 1 to infinity of e to the ix, okay, which is just, okay, the same as cosine theta. I'm sorry, if it's in terms of x, is cosine x, and then plus I sine x. So we could represent it as the series of cosine x plus I sine x, all of that to the power of 2k minus 1. So that should be the answer, the whole answer, right? If we were to split this into two, well, you say this is the top part and this is the lower part, the lower portion. And yeah, that's what the series representation should look like. And they use some, you know, Laurent series, which is like something way above my mathematical scope. So, well, that was pretty fun. I'm going to show you the video now. So here it goes. Okay, so over here we have our function cosecant of x. And then we have the function, the series expansion, right, with just one term each. We have the sum, okay, from n equals 0 to 1. And then we have the inner sum, which is just sine of x, right? And as you can see, it's starting to, okay, try to approximate the value of cosecant of x over here. But it needs more terms. So let's try to add more terms over here. So suppose we want to add, okay, so let's see. Let me add, okay, let me add up to 5 terms over here and see what happens. You see, it gets even better and better. The approximation gets better around this points over here. But the inside, okay, needs more terms. So what if we add, say, 10 terms? Well, nothing much changed. What it does is it completes the other functions, or the other parts of the graph, because it just goes up to infinity. So really, sine of x is just accounting for the infinite number of curves over here. So let's add maybe 20, okay? But then it's the sine of x part doesn't really help us get a, okay, sharper, get a steeper curve. So we gotta add more terms to the outer sum. So say we want to add 10. See, it gets even better. So as that goes to infinity, all of that is just going to account for the top part of the function, right? That's just going to account for the top part over here. But now, what if we do, okay, say we want to do the same thing. But now, instead of writing the expansion for sine of x, we just write, you know, sine of x.
and see if we can account for all values. Okay, for all curves. So let's see. Okay, so say we want to get just sine of x. So let's do sine of x over here. Okay, so this is lagging a little bit because Desmos can handle this. Okay. Now, as you can see, it's actually accounting for all the curves on the interval from negative infinity to infinity. But it's still not a exactly perfect approximation, right? It's not the same curve because, well, we need an infinite amount of terms over here. So if we add, say, 20, it's going to get better and better, right? And then if we add 30, it's looking even better. So, that's the point. But now, say that, we want to account for the lower part. So as I showed you, we just do the same thing, but then we multiply it by -1, right? So let's make a duplicate of this. And then let's multiply it by -1. So you see that we shifted down. We reflected about the x-axis. And then we make a transformation. We shift the graph pi units to the right. And then there you go. Okay, this is going to be your series expansion. And of course, that's not 30 terms. Imagine it's just infinity, right? But Desmos, can't handle infinity. If we write infinity, it just says summation bounds must be finite numbers, right? And if we write a really, really big number, it's just going to crash. Okay, so let's say 1,000. See, it just froze up. So it's usually not recommended to do that. All right, so yeah, that's it for now.
All right, so I hope you liked the video. Thanks for watching. Please subscribe, leave some comments if you wish, right? Check my work, you never know. Sometimes I could make a little mistake, a little typo, but that's all right. All right, I'll see you next time.